All right, so in-class buoyancy number 4, similar to the lab on Monday. So, number 4, it says a group of penguins want, man, I gotta fix these typos. A group of penguins want to stand on the iceberg, on an iceberg that is 4 meters wide, 6 meters long, and 2 meters tall, and has a density of 917 kilograms per cubic meter. The iceberg is floating in salt water, which has a density of 1,025 kilograms per cubic meter. How many 42 kilogram penguins can fit on the iceberg before they get their feet wet? So, I already kind of have my picture drawn, but the idea, I guess I can redraw my penguins. They were pretty good, I didn't want to, but okay, just for you. Nothing but the best for you guys. You guys don't get leftover drawings, you get originals. That means I should read the entire thing. All right. So we have a rectangular prism, perfectly shaped iceberg floating in the ocean. That's 4 meters by 6 meters by 2 meters. And if that was the only thing, the water level would be about there. Okay, I'm going to erase that little blue squiggly line in a moment. But what's going to happen is there's these penguins, and these penguins don't want their feet to get wet, so they climb on the iceberg. And then when they climb on, it gets a little bit deeper. And then another penguin climbs on, and it gets a little bit deeper. And another one, and another one, and another one, until either they run out of room, or their feet get wet, and they don't want to get their feet wet. But the idea is every time another penguin climbs on, it's going to get a little bit deeper, until the water level is like right there. It's right on the cusp of coming over and getting their feet wet. What we're trying to figure out is how many penguins can climb on that iceberg before it comes over the top, before their feet get wet. So if we go through and we look at forces acting on this iceberg, hopefully you're all getting to the point that you recognize, since we're talking about buoyancy, that there's going to be a buoyant force, and that buoyant force is going to be upwards. In addition to that buoyant force, there is the weight of the iceberg, right? Because the iceberg in and of itself has some weight, and that's why I drew that original blue line, because the weight is going to push it down the water a little bit. Then every time another penguin climbs on the iceberg, trying to get away from those orcas, those killer whales, those orcas, to get away, yeah, that's why they're climbing on. That sinks a little bit deeper and a little bit deeper and a little bit deeper. And every time a penguin climbs on, there's going to be an FG of a penguin. Now I'm going to erase this in a second, but look, oh look, one penguin climbed on. There's FG of a penguin. Oh look, a second one climbed on. I'm going to erase this in a second. There's another FG of a penguin. Oh look, a third one just climbed on. There's another FG of a penguin. But that gets really, really messy. So what would be a better way to represent FG of 3 penguins? I'm just saying 3 because I drew 3. Well, we would say, well, there's 3 of them, right? But I don't have 3. I'm going to erase that in a second now too. But if this was my picture, I'd just take the FG of 1 penguin and I'd multiply it by 3. But how many penguins do we have? So how can we represent that? Algebraically, how could we represent it?
X.
As X. Okay, how many penguins are there? There's X many penguins. And we're solving for X. Okay, we're going to solve for X. Any other forces I missed? I think we're good. This will become a Newton's second law problem. Couple ways you can get to that, when you can substitute numbers in to Newton's second law, or you could substitute equations into Newton's second law. But I think most people kind of like to individually kind of multiply and figure these things out first. So if we pull those, if we calculate the numbers that we can, then we're plugging numbers into Newton's second law. So if we start with penguins, Fg of a penguin can be calculated if we take the mass of a penguin and multiply by g. So the F of g of a penguin is 42 times 9.8. The F of g, let me fix it. F of g of a penguin, the F of g of a penguin is 42 times 9.8 is 411.6 newtons. But how many penguins are there? X many. Yeah, X many, you're right. So here we'd say it's X times 411.6 newtons, right? Because we have X many penguins, each penguin is 411.6, and we have X many of them. We're going to solve for X. We'll solve for X. My buoyant force equation, FB, is equal to the density that's being displaced times the volume that's being displaced times g. And I'm writing it in the original form to try to emphasize that displacement part. So it's the density of the fluid that's being displaced. What is the fluid that's being displaced by this iceberg in penguins? Salt water, yeah, salt water. Right? So when we plug numbers in, it's the density of the salt water, which this time, I don't know why I did, but I said the density of that salt water is 1,025. Other times I've given you 1,020. I don't know why I changed it on you, but whatever, I did. So it's 1,025. This volume that's being displaced, the idea of this volume being displaced is how much of that iceberg is underneath the surface. And the quick answer is all of it. Good. All of it's underwater. So when I say how much water was displaced, well, the amount of water that was displaced, salt water that was displaced, is equal to the amount of the iceberg that's underneath the water, and all of it is under the water. So these dimensions, how much we multiply the dimensions that are underneath the water, so that's 4 times 6 times 2. That's going to give me the volume that's being displaced. Okay? And then, don't forget to multiply by g, which is 9.8. So when we go through and we multiply all of those together, for the record, this is big. This is a very large number. It's also a pretty big piece of ice. If you think 4 meters is about 12 feet, 6 meters is about 18 feet, 2 meters is about 6 feet, so it's a pretty big block of ice floating in the water. So we go 1,025 times 4 times 6 times 2 times 9.8. Don't forget that 9.8. We get a buoyant force of 482,160 newtons. Check to make sure I inputted that right. Yes. Okay. So this is 482,160 newtons. And one more number we have before we start plugging in Newton's second law. And the Fg of the ice is simply the weight of the iceberg. And all we have to do in order to get F of G of the iceberg is multiply the mass of the iceberg times 9.8. But did I give you the mass of the iceberg? But how can we find it? using which equation?
Density equals mass divided by volume.
Yeah, so if we use the density of the iceberg is equal to the mass of the iceberg divided by the volume of the iceberg, we can solve for mass, like I've asked you to do many times. And the density of this iceberg said it was 917, which is equal to the mass of the iceberg times the volume of the iceberg. Now this is the total density of the iceberg, so we got to use the total volume of the iceberg in order to calculate the total mass of the iceberg. I'm just trying to emphasize. So it's the total volume, it's 4 times 6 times 2 will give you the volume, which is 48. So if we take 917 times 4 times 6 times 2, we get a mass that's equal to 44,016 newtons. So the weight, is that the weight? Is that the F of G? No, that's the mass. So make sure we multiply mass by 9.8 to get 431,356.8 newtons. All right, I think we have just about everything we need. Now we're plugging it into Newton's second law. Well, actually, we got to build Newton's second law first. So if we build Newton's second law says the sum of all my forces is equal to F net, which is equal to mass times acceleration. It's floating on the surface, so velocity is constant, acceleration is 0. Newton's second law says I add my ups, there's only one. I subtract all of my downs, so I'm going to subtract Fg of the iceberg. I'm going to subtract x times the Fg of a penguin, and that's equal to 0. Now I said F of G of penguins times x. You could do it otherwise. You could go through and calculate the total F of G that it can hold and then divide by 411.6. I think this approach is probably just as good though, or just, I like this a little bit better actually. I'm going to want to get my x by itself, so this is a minus sign. So I got to add it to the other side, which then we add x times F of G of penguins to the other side, we get it's going to be equal to that. And then we plug numbers in. 482,160 minus 431,356.8, which equals x times 411.6. Okay, so then I take 431,000, oops, I don't have that one. All right, so I take 482,160 minus 431,356, and that gives us like 50,803. And then I'm going to divide right away by 411.6 to give us the final answer of x is equal to 123.4 So I mentioned that why are these penguins climbing on the iceberg? Because there's an orca chasing after them, trying to eat them. So assuming 0.4 of the penguins is not a possibility, unless the orca only eats 0.6 of it, we're talking whole penguins. So how many whole penguins can this iceberg hold? Now this kind of is looking at that final question. Okay, so 123.4 is that cusp. Like that's right on that edge of coming over the top. So if they don't want their feet to get wet, how many whole penguins can it hold? Do I go up or down? Down, right? Yesterday with Russell and the balloons, we wanted him to float, so then we had to round up. So you just make sure you're kind of looking at that final question or that final answer. And in this case, we're trying to keep their feet dry, so the total number of penguins that can fit on this iceberg without their feet getting wet is 123. That's the number. So your lab on Monday, we're going to build a boat. Most people don't build a rectangular boat. If you did, you could go length times width times height, but most people don't. So the approach to calculating the volume of your boat is similar to the volume that we used for the displacement of the helium balloon yesterday. So if my helium balloon can hold 0.03 cubic meters of helium, that was from the problem yesterday, we also said, well, that must be how much air that balloon displays. So because most people are going to make an irregular shaped boat, in order to calculate the volume or determine the volume of that boat, we actually fill the boat with water. And if we can determine how much volume that boat can hold, then we can say, well, that's how much water our boat is going to displace. So we're going to use like that idea. And instead of solving for how many penguins, we're going to solve for how many pennies. I have 5 my pennies. So that's how we're going to approach these. Okay, so it's a calculation similar to this that you'll have to do. We'll have an experimental value. You're actually going to test to see how many pennies your boat can hold. And you're going to calculate your theoretical or accepted value of how many pennies your boat should be. And then you'll compare it. So that's Monday's lab. The rest of today is your time to finish up that worksheet called Buoyancy. Some people have already submitted that, and I appreciate that, and I graded a couple of them already today. If you don't have that done, they're due Sunday. Due Sunday, but take care of it now, then you don't have any homework over that 3-day weekend. So, if you have questions, let me know.